Okay, so we're going to talk about chemical bonding. And a chemical bond is just when an atom's valence electrons get pulled toward the nucleus of another atom. Just a very broad way to define a chemical bond. And we're going to get into more specifics here as we go. So if one of those two atoms that are interacting has a low ionization energy, then it's going to give up that valence electron, or it could be multiple valence electrons, and that's going to result in an ionic bond. If neither can really easily lose an electron, then they're going to end up just sharing. And so we call that a covalent bond. And you can see that there with chlorine, two chlorine atoms sharing valence electrons. And that's because neither of them is capable of really giving up electrons. Okay, so forming ionic compounds. So let's take a look at sodium and chlorine. So this is going to form sodium chloride, which is table salt. They both have 3 energy levels, and they're both found, if we look at the periodic table, they're both found in the 3rd period, which means they have 3 energy levels of electrons. Sodium is larger because it has a smaller effective nuclear charge. And also because it has a smaller effective nuclear charge, it doesn't hold on to its valence electrons as well. And so chlorine having a spot out here for one more valence electron because it has 7, and it has this effective nuclear charge of 7, is going to have a really strong pull on sodium's electron. So basically it just takes it. And when it takes it, what we've done now is sodium, which has 11 protons before and after losing an electron, started with 11 electrons. So 11 protons, 11 electrons, that's why we don't see any charge written here. But now, after losing an electron, it still has 11 protons, so now it's only got 10 electrons and has a positive 1 charge. Chlorine, on the other hand, is going to gain an electron, and so chlorine, which started with 17 protons and 17 electrons, now has 17 protons and 18 electrons, and so it has a negative 1 charge because, of course, electrons are negative. So these ionic bonds always form between a metal and a nonmetal, and that is because an ionic bond is a transfer of electrons. And in order for us to have an element that's able to give up electrons, it has to have a really low ionization energy, and of course that means the left-hand side of the periodic table. Generally speaking, the lower left-hand side of the periodic table. So if we look at our metalloids from boron on down to the right here, everything to the left of that, with the exception of hydrogen, is a metal, and so they have low enough ionization energies to give up an electron. And you can see here on our table of ionization energies that it's not just like a sudden drop off, it's a gradual drop off. So when we say that an ionic compound forms between a metal and a nonmetal, that's the rule we're going to use. But it is important to kind of note that it's really sort of a gradual distinction. That, in other words, even though, for example, germanium or let's say gallium could be considered a metal, it's really not a whole lot lower in ionization energy than, let's say, selenium or tellurium, which we might consider to be a nonmetal. Okay, so next we're going to talk about drawing Lewis structures for ionic compounds. Let's use as an example the compound magnesium oxide. First thing I want to point out here is the "ide" ending on oxide. So we don't call it magnesium oxygen. When it's an ionic compound, you just give an "ide" ending. It's very simple. And it's always the non-metal that gets that "ide" ending and the metal that gets listed first. So this magnesium oxide is metal, non-metal, and the oxygen, the non-metal, gets the "ide" ending. Okay. Okay, so let's take a look at what a Bohr model might look like for this guy. So this is magnesium. It has 12 protons, so it has a plus 12 nucleus, and it has 12 electrons, so it has no overall charge. And then over here we have oxygen, which has 8 protons in its nucleus, and it has 8 electrons, so it also has no charge. Neither of them has a filled outermost energy level, so they both have room for more electrons. Magnesium only has 2 electrons out here in its third energy level, so it's got room for 6 more potentially. Oxygen, on the other hand, has 6 in the second energy level, so it has room for 2 more. Okay. So the question becomes, all right, if these two are going to bond to form magnesium oxide, what's going to happen? And the thing that we would expect to happen is whichever element is more is a stronger pull on electrons and has a higher ionization energy, meaning it's harder to pull away its electrons, that is the one that's going to gain electrons. So if we look at oxygen and we look at magnesium, magnesium has an effective nuclear charge of only 2, whereas oxygen is 6. So it has an effective nuclear charge of 6. And it's also a much smaller atom, or at least one entire energy level smaller. So we would expect essentially oxygen to be able to grab the electrons and pull the electrons from magnesium's outermost shell, its valence shell, to it. Okay, and when it does that, it's removing this guy, this one up here, and this one over here on the left, and that's going to fill up oxygen's second and outermost energy level, and it's going to make oxygen have a an electron configuration that's just like the noble gas neon. And that also means that it's full, so it can't really accept any more electrons in that outermost energy level. Magnesium, on the other hand, is also full, because even though it lost electrons from its third energy level, now its outermost ring would be the second energy level, and it would have it would also have 8, so it would be full, and it also would resemble neon in terms of its electron configuration. Now understand that neither of these things have turned into neon. They just happen to have the same number of electrons as neon, and they now have an outermost shell, which makes them unreactive because they don't have any place else to put electrons. Okay, but when that happens, that's going to do something to our charge. So if I draw my Lewis structures for magnesium and oxygen, one way to signify what's happened here, instead of drawing the Bohr models, is I can just draw my original Lewis structures. So that would give me 2 dots or 2 valence electrons on magnesium and 6 on oxygen. And then what we're going to see happening is those 2 electrons from magnesium, as we described a minute ago, are going to just get transferred over to oxygen. So they disappear from magnesium and they show up on oxygen. And it looks like magnesium has lost all of its valence electrons. What has in fact happened is it just lost all of its valence electrons from what used to be its outermost energy level, which would be 3. But now it has 8 valence electrons in the second energy level. It also means that it has a +2 charge, because as we talked about initially, it had 12 protons and 12 electrons, but it lost 2 electrons, and since electrons are negative and it has 10 negative particles and still has 12 positive particles, that would add up to a total charge of +2. Oxygen, on the other hand, has done the opposite. It has gained 2 negative particles, so now it has 10 total electrons to go along with its 8 positive protons for a total of -2. And the last thing you'll see done on these Lewis structures for ions is you always want to put brackets around the Lewis structure for the negative ion, which in this case would be our oxide ion. And then since these guys are present in a 1-to-1 ratio, we would basically just say that this is MgO. That's the chemical formula for magnesium oxide. Okay, let's try another example. Strontium chloride. So the first step is going to be to draw the Lewis structure for strontium. And so I am going to do this, let's see here. We'll put a couple dots just right here on the right and maybe up top. And then for chlorine, I'll just keep the same color here, and we'll go with 7, right, because it's in group 17, so it's got 7 valence electrons. We don't really need to draw the Bohr model or talk about, ionization energy and all that stuff, because we've kind of already established that it's the strontium, the metal, that has a lower ionization energy. It's way over here on the left-hand side of the periodic table. And so it's always going to be the metal that ends up giving up its electrons. So strontium has 2 that it can lose. Chlorine, though, if it gains just 1, it's going to be full, right? It's going to have 8 valence electrons. And so what I'm going to go ahead and do is draw that 1 electron as a little X. And the only reason I'm drawing it as an X is just to show that it didn't start off with the chlorine atom. It got transferred there. Then we're going to go ahead and erase one of them from strontium. So maybe just get rid of this guy up here. But strontium still has one left, right? So what we have to do is bring in another chlorine to take that, that last strontium electron. So chlorine, I'll go ahead and draw it with its original 7 valence electrons. And we know that it can hold 1 more, and that's how many more strontium has to give, right? So we'll go ahead and get rid of the electron over here on strontium. There we go. And we're going to add it to chlorine. Again, just drawing it as an X just to signify that that was not originally one of chlorine's electrons. It's not actually a different electron. An electron is just an electron. But chlorine has gained 1 electron apiece, so they're each -1, and strontium is +2. And so then our formula now is going to be SrCl2. Okay? All right, let's try one more. This one's going to be aluminum sulfide. Aluminum sulfide. So go ahead and see if you can, pause and stop and write the Lewis structures for aluminum and sulfur and see if you can figure out what's going to happen. Okay, so aluminum would start with 3, right? And sulfur would start with 6. And sulfur, being the non-metal, is the one with the greater ionization energy. It's going to be the one that takes electrons instead of giving. And so sulfur, though, only has room for 2 more. So we'll go ahead and erase 2 of these 3 aluminum electrons. And we'll go ahead and just throw them on here as X's on wherever there are spaces. And there are 2 spaces there on sulfur. And we'll go ahead and draw the brackets, and this would be a -2 charge, right, because it gained 2 electrons. But now that means I'm going to still need to bring in another sulfur. For some reason, that's an aluminum. Bring in another sulfur, and its 6 valence electrons are there, right? And so this guy has a high ionization energy. It's good at attracting electrons, very poor at giving electrons. So it's going to go ahead and take that last electron away from aluminum, and we're going to go ahead and just attach it here where it is needed on sulfur. I am going to go ahead and just give this aluminum its +3 charge, because if you remember, it lost 3 electrons total, so now it has a +3 charge. And aluminum, by the way, if it lost 1, 2, 3 valence electrons, it would also resemble neon in terms of its electron configuration. Now this sulfur needs to gain 1 more electron. That's why we had this other aluminum pop up. Now, when aluminum comes in here, it's going to have 3 valence electrons, not 1. So it's going to be able to supply 1 valence electron to sulfur, because that's all sulfur has room to accept. Okay, and I'll go ahead and draw brackets around this sulfur and put its charge, which is -2. All right, and then the very last step, as you might have guessed, is going to be to bring in 1 more sulfur with its 6 valence electrons. And it is perfectly equipped to accept both of the remaining 2 electrons from aluminum. So I'll go ahead and erase them from aluminum. and we will stick them onto this sulfur. And now aluminum is happy, so it has a 3+ charge. And then sulfur is happy, and we would of course call it sulfide now because it's got a negative charge, and that's what we call negative ions. And there we go. We've got 5 ions, 2 positives and 3 negatives. And so our formula would be Al2, because we have 2 aluminums, S3.